Hey everyone, and welcome to this explainer. I'm really thrilled to have you here. If you're a focused learner trying to piece together the mechanics of our modern world, well, you're definitely in the right place. Today, we're diving into a massive, multi-billion-dollar question about the future of energy storage. What exactly is going to replace lithium-ion? We literally see these batteries everywhere, but the technology is hitting a wall. The race to build the next generation is absolutely fascinating, so let's get into it.
Look, it's an undeniable fact that lithium-ion batteries power a huge chunk of modern life. I mean, they're running our phones, our laptops, our electric cars, and even those massive grid storage systems. But they are hitting their hard physical limits. They age, they heat up, and over time, they just degrade. So the big question staring down the entire energy sector right now is pretty simple. What comes next? What's the technology that's going to take the baton and actually push us into the future?
Chapter 1. The Lithium-Ion Reign. Let's look at how we got here.
To figure out where we're going, we kind of have to understand why lithium-ion became the undisputed king in the first place. It basically solved a really hard problem incredibly well by packing rechargeable energy into a tiny space. But just take a look at this chart. It brilliantly illustrates the explosive, compounding demand we're dealing with today. That massive orange wedge, that represents electric vehicles. Combined with stationary grid storage, the projected global capacity requirements are soaring well past 500,000 megawatt-hours. We are demanding more from our batteries right now than at any other point in human history.
But here's the catch. This boom has completely exposed some dangerous geopolitical bottlenecks. As you can see on this map, the raw materials needed for lithium-ion, specifically cobalt, nickel, and lithium, they're concentrated in just a handful of regions. For instance, a massive percentage of the world's cobalt comes from the Democratic Republic of Congo, and a ton of the natural graphite and aluminum smelting is locked down in China. It creates a severely fragile supply chain, which is terrifying when you're trying to literally electrify the entire globe.
So beyond those supply chain headaches, the crucial point here is that lithium-ion has physical flaws, real, practical flaws. Under stress, they carry terrifying thermal runaway and fire risks. They also suffer from inevitable capacity degradation over time, basically internal chemical buildups that researchers call SEI growth. Plus, because they rely on those constrained raw materials we just talked about, figuring out end-of-life recycling isn't just an environmental necessity, it's an economic one. And frankly, we haven't quite mastered it yet.
Chapter 2. Building a better battery. Let's head into the engineering lab.
You know, good enough is definitely not the same as perfect. When we look at what it actually takes to dethrone lithium-ion, it's a tall order. To win, a new battery needs to be safer, ideally with zero flammable materials. It needs to be longer lasting, cheaper to mass produce, incredibly fast to charge, and hold a higher energy density. But here's the reality check. It is practically impossible for a single new chemistry to check every single one of these boxes at once. Engineering is always a game of trade-offs.
Chapter 3. The Solid-State Promise, the hyped-up game-changer.
Okay, let's talk about the absolute darling of the EV world right now, the solid-state battery. By comparing these two architectures, it's pretty obvious why everyone is so excited. Traditional lithium-ion uses a liquid electrolyte to slosh ions back and forth. But that liquid, it's highly flammable and prone to leaking. Solid-state literally replaces that liquid with a solid material. Boom! Changing that state of matter drastically boosts safety by entirely removing the fire risk. Plus, it actually allows engineers to use lithium metal anodes, which massively increases the energy density.
But we really have to ground the hype here. It is one thing to make a flawless, tiny solid-state coin cell in a pristine, climate-controlled lab. It is an entirely different beast to scale that up to millions of affordable, large-format units for cars. Right now, solid-state batteries are facing immense scalability challenges, and the manufacturing is highly complex and really expensive. So yes, they are incredibly promising and they are coming, but they are not dropping into every consumer car tomorrow.
Chapter 4. Sodium-ion and Beyond. The push for cheap and abundant.
Since solid-state is so pricey right now, what if we prioritize cheap abundance instead? Enter the sodium-ion battery. And yeah, it uses the exact same sodium salts you literally have sitting in your kitchen right now. Now, sodium ions are physically larger and heavier than lithium ions. Because of that, these batteries have a lower energy density, meaning they're way too bulky to stick in a sleek smartphone. But they're absolutely perfect for massive, stationary grid storage where physical weight just doesn't matter, and keeping costs at rock bottom is the main goal.
And as this table brilliantly illustrates, every other contender out there comes with a major trade-off. Take redox flow batteries. They store energy in massive liquid tanks. Amazing for the power grid, completely useless for your car. Zinc Air uses oxygen straight from the air, so it's super light and cheap, but it really struggles with being recharged over and over. Even good old lead acid is cheap for backup power, but it's heavy, toxic, and dies quickly. Every single alternative chemistry demands a compromise.
Chapter 5. The Scaling Challenge. The Grueling Realities of Manufacturing.
So why haven't these awesome alternatives completely taken over yet? Well, it all comes down to manufacturing scale and what happens at the end of a battery's life. Check out this battle happening right now within the lithium-ion family itself. On one side, we have NMC batteries. They use expensive nickel and cobalt. Because those metals are precious, recyclers actually want them. It's highly profitable. On the other side, we have LFP, or lithium iron phosphate. LFP is amazing. It's safer, super durable, and way cheaper because it ditches the cobalt. But that accidentally creates a huge paradox.
Look at this quote from industry experts. It really hits the nail on the head. If an LFP battery is too cheap to profitably recycle, what on earth do we do with it? Without those high-value metals inside to subsidize the cost of tearing them down, LFP batteries might just become permanent environmental waste. That is, unless we mandate strong circular economy rules or invent much cheaper recycling technologies like direct recycling.
Now, another great idea is giving old EV batteries a second life by hooking them up to the power grid. Brilliant, right? Well, operators are hitting massive roadblocks. They are completely blocked by a lack of digital tracking. Imagine trying to buy a used car without an odometer or any service history. That's exactly what buyers of used batteries are dealing with. Missing state of health data, totally non-standardized packs glued together with random adhesives, and zero digital tracking. Without a proper battery passport, repurposing them is just a massive risk.
Chapter 6. The Battery Toolbox. Pulling it all together.
All right, let's pull all of this together to answer our very first question. The absolute crucial point to take away from this explainer is that lithium-ion will not have one single successor. There is no silver bullet here. Instead, the future of energy is going to require a diverse toolbox of specialized chemistries perfectly matched to specific jobs. Solid state might win out in premium electric sports cars. Sodium-ion could completely dominate the power grid. And honestly, lithium-ion will probably keep powering our phones for years, but the next generation of batteries will need to be safer, smarter, and cheaper.
Lithium-ion completely changed our world, but it's definitely not the final answer. As this entire industry shifts from a one-size-fits-all monopoly into a complex, specialized toolbox, you really have to wonder, which of these fascinating new chemistries will be sitting in your driveway, powering your smartphone, or keeping the lights on in your house in the next decade? Thank you so much for joining me on this deep dive. Keep learning, and I will catch you in the next explainer.